Our next talk is entitled R-HOPE, Development Approach to Extreme Non-Volatile Memory Reuse on Board the Curiosity Rover by DJ Byrne, Alexandra Holloway, and Nick Pepper of NASA JPL. All right, it's all yours.
Hi, can you hear me?
Yes.
Awesome. I'm Alexandra Holloway. Today we're talking about R-HOPE, the development approach to extreme non-volatile memory reuse on board the Curiosity Rover. Earlier we talked about software updates. Well, here we go. Next slide, please. The agenda for this talk, we're going to talk about the situation, the approach to fixing the situation, the approach architecture, some details about the development, and some lessons we encountered and maybe learned. I'd like to point out that the software development team for R-HOPE, which is the release that we're going to be talking about, was very small. It was only 5 people, but we did have a bunch of support from other folks, both as consultants and V&V. Next slide, please. Just a quick introduction, the Curiosity Rover hardware software setup. Curiosity has been on the surface of Mars since August 5th, 2012. It was launched in 2011. So it's been running for quite some time. And how old is your laptop that you're using? We get replenishments every 2 years or so. But we haven't had a replenishment on Mars. Curiosity has 2 rover compute elements called RCE-A and RCE-B. The prime one runs the mission, and the backup one only boots when the prime RCE fails, and then it takes over. And the highest priority, if that were to happen, is always fixing the failed RCE so that we continue having both. We have identical hardware and software. Each of the computers has its own RAM, its own flash memory, and they are cross-strapped to the radios, and the configuration files and parameters are kept in sync. Next slide, please. A quick approach architecture. This is the physical RCE-A. I'm pointing out the non-volatile memory here. We've got the NOR memory on the left and the NAND memory on the right. The NOR memory is really small. We've got 32 megabytes for each of these 4 zones, and each zone holds a flight software executable image. And then for the NAND memory, we've got a lot more space, about 4 gigabytes, which holds the entire file system, the engineering partition, the data products partition, and the two copies of the non-volatile parameters. Next slide. So we're going to focus on the non-volatile memory. What we saw is progressive failure of the non-volatile memory on RCE-A. And we had to enforce some operational workarounds and some software workarounds. The goal was always to preserve as much of the non-volatile memory as possible. We're talking about the NAND memory with minimal software changes, because of course we can't fix the hardware. There's no second rover that can come and swap out the chip. So in the beginning, software mapped out the bad memory. So we reduced that from 4 gigabytes to 2 gigabytes. So RCE-A now had half of the NAND memory. But finally, hardware issues were so bad that we couldn't use any of the NAND non-volatile memory on RCE-A. So the question is, what if RCE-B fails? So let's say that we're on RCE-B, that's prime, something happens, we have to swap over to A, and we have no NAND memory. So that's the problem setup. Next slide, please. What we want to do is have a lifeboat for RCE-B. So when we swap over to RCE-A becomes the lifeboat for B if we have to swap from B to A. What we developed is something called R-HOPE. The R stands for release number. And hope means, gosh, I hope it works. And our hope would make RCE-A safe for safing. So if we have a safing event on RCE-B, we swap over. Our hope aims to maintain control over the thermal, power, communication, and all these necessary things that we really want to continue using. We want to be able to store recorded telemetry so that we can downlink it later. We want to execute sequencing and fault protection. So what we need is a file system, and we need parameters somewhere else. But where? Remember that the file system is 2 gigabytes on RCE-A following those issues we had earlier. And so where can we find so much space? We can't. We can't find 2 gigabytes. What we do have is the NOR memory, but it's tiny. Next slide, please. So if we were to put our file system on NOR, here's what that would look like. The 2 gigabytes that we used to have now becomes this little teeny bitty part of the actual size of NOR memory. And if we were to zoom it in, that's kind of what it would look like. So the partition size reductions, we would reduce the parameters by 63%, engineering partition by 83%, and the data products partition by 98%. Next slide. So now I'm going to turn it over to DJ, our primary developer, to talk about design and implementation details.
All right, next slide, please. That was 2 slides forward, I think. Or no, okay. So the before and after picture is, I want to focus on that data storage layer. The MSL software was very well designed, very well implemented, but not by us. I was enjoying Mr. Thibault's keynote speech because he seems to have already hit many of the themes we want to. The last time the software was updated was in the year 2014 and not by us. So yeah, he was right about all of those points. In the before times, they did a very excellent job of building abstraction layers so that pieces could be swapped out. They leaked a little bit. And so we didn't have to change much in the file system or the parameters as used by the spacecraft itself. We didn't remove, in our hope, any functionality despite that drastic reduction in space. It still has all of the capability it ever used to have. It's just that we didn't test things we knew would consume a lot of space. And Nick will talk more about the operations considerations later. At the data storage layer, it was meant to be agnostic to the type of non-volatile memory beneath it. Remember, MSL was being developed, the software and the hardware simultaneously, and there were active discussions about, well, we think we're going to use this chip, maybe we'll use that chip. They did a very nice job of saying, well, look, we need a read and a write and an erase and a copy, but we'll be agnostic to what's underneath. But then over time, that abstraction layer leaks a little bit. And so the data storage layer kind of knew it was talking to a NAND chip, and it kind of knew that a NAND chip had blocks you could erase. A 0.5 megabyte of space is the thing you would erase. And each of those 0.5 megabyte blocks held 64 pages, each of which was 8 kilobytes, and each of which had a header describing it, which came for free. The headers are in non-addressable spaces for the pages. And so it kind of knew that, and if it wanted to write 8 kilobytes of data, it knew it was really saving more than 8 kilobytes, but it didn't have to address it. So what we did in our hope was add a translation layer below the data storage, which let it believe it was still talking to this odd pseudo hardware, but direct all of the actual data saving into another chip. Next slide. All right, so the development effort itself, because we were not the original developers, we broke it into 3, later 4. We added a version 0 because it's a software element. Version 0 was make sure we understood our baseline. Where are we standing now? If we run the unit tests, do they pass? And just capture all of those outputs so that we could compare them later. When I change the code and we rerun the test, do we get the same result? Or at least is the difference something we expected and anticipated? Part of the challenge for that was that our configuration management system had to maintain the R12, which is on Mars today. And R13 was in development simultaneously by another group of developers with some overlap. I was not working on R13, but so my configuration management system had to not interfere with what they were doing. So that took a little more effort than we kind of thought up front. Version 1 that was try to get as much development as we can before we lose our simulation environment, which we'll talk about later. So step 1 is just use the same NAND chip on our test bed at JPL, but shrink how much of it we use down to the 64 megabytes instead of 4 gigabytes, and find out where that ripples. And we found many places where that rippled. In particular, a lot of the margins that the software keeps here and there were greater than our total capacity now. But we had all of the this tooling and the infrastructure that we could do a software simulator doing all that. And then version 2 was take the big step and actually swap out what the hardware is doing. I should mention in version 1, we also pulled in a lot of software patches from other missions. MSL, as I said, the software is from 2014. But since then, Mars 2020 has inherited the software. The software has been used by SMAP and other missions who have found bugs here and there. We didn't pull in all of the bugs, but anything having to do with the non-volatile memory we did. Because if it was a small, unlikely to hit you bug over 4 gigabytes, the probability of hitting that would be much larger when we're reusing the same storage area over and over again. And there's a version 3 that has its own slide where that's where we kept the development on track by always having a, hey, I've got a bright idea to make this better. Good, write it down, don't, and get back to your priority. Next slide. So we'll talk a little bit about those margins. For capacity planning, we have to have a certain number of parameters. On MSL, because they were developing all of the software simultaneously, they didn't know how much space the parameters would take. We now have years of experience. We could shrink the actual storage space for parameters way down to what was actually needed and just throw away most of the margin. Nick Pepper had to do a lot of the analysis for that and still guessing how much margin do we need to keep around. So that reclaims some space. Likewise, the partition for engineering files, these are files that are only uploaded from the ground. The spacecraft does not write in that area. And those are where your recovery and lifeboat functions live. How much of that space has actually been used? How much margin can we recover? And that leaves the question of, okay, whatever's left is for science. How much is that? Next slide. So that was version 1's challenge. And we hit a lot of lessons there. On version 2 is when we swapped out the actual hardware. Now at that data storage layer, again, it kind of knows it's talking to a NAND chip. So we had to map between the concepts of a NAND block and page into the NOR chips concepts of zones and sectors. Deal with that those hidden headers somehow. And the NOR chip also doesn't have one consistent sector size. It's got small sectors and big sectors, unlike the NAND chip, which only has one size of block. So deal with that. Also for copying, the software knew there was a hardware function for within the NAND chip itself for copying a page. So it would just say, oh, make a copy of this page. And we would have to obviously emulate that in software. Next slide. I'm running through these very quickly. The actual slide presentations, when you download them from the website, have a lot of the hidden slides with more detail. On this slide, we're just showing before and after. At the top half is the NAND. How does it work? And the device, we didn't change, of course, the NAND device driver, because why would we? And we didn't change the NOR device driver. It was just all the work is in that green box on the second part, where we're going to use the NOR in a way it hadn't been intended to. And we'll focus on that a little bit more on the next slide. So that's just a comparison. And here we see, I'm going to, on erase block, because the software kind of knew it had blocks, it always wanted to erase half a megabyte at a time. But the NOR sectors were either 16 kilobytes or 128 kilobytes, depending on where you were addressing. So we had to take a page number, convert it to a zone and address, and then have some concept for what is the thing I can erase. And we started going through acronyms or synonyms. We couldn't use the words block, page, zone, or sector because those already had meanings. We couldn't use the words segment, chunk, box. We gave up and called it a fascicle because that word didn't appear anywhere in the documentation or the software, and we would never get it confused with any of those other concepts. Okay, next slide. Very good. When writing and reading to the chips, the software goes through a firmware layer that's using direct memory access, so that the CPU will set up a buffer, a DMA safe buffer area, and then tell the firmware, hey, read this and save it in that page, or read that page and save it in this buffer, which is great as long as those headers are hidden from you, because on our hardware, the DMA pieces, the smallest thing you can allocate is 4 kilobytes. Hey, but a page is 8 kilobytes, so that maps in nicely until you add the 256 bytes, and suddenly you don't have all these alignments, and you had to pay attention to that. We needed another scratch pad. The lesson on this slide is when we were looking for a little spare RAM to use as DMA scratch space, where we carved it from, we got a little bit lucky. We found a relatively unused sector at the end of the memory map. One of the early iterations, we were going to grab a section out of kind of the middle of the memory map, but that shifts the locations in memory of all the DMA segments used by every other module. And you have to worry a little bit about, gosh, I wonder if that other module that I'm not familiar with hard-coded something that I'm about to move. Kept me awake a couple nights. Next slide. All right, and then version 3 was our parking lot for, there's no way this thing's gonna work. We're gonna need more space. I hope it worked. We put it in the name, but hope is not a plan. And so we kept really clever ideas for can we save another megabyte here? Can we save a few megabytes there? And it turns out we didn't really need to do any of them because Nick Pepper, next slide, is going to talk about why version 2 was good enough and we could stop.
All right, great. I think you can move directly to the next slide. So the short answer to the question is that we tested it. So sort of by necessity of our constrained timeline, most of our RHOPE test procedure development, as well as a lot of the testing, was conducted in conjunction with our code development. So almost a day-to-day feedback loop of development, building the sandbox, and then testing it on either the software or mostly hardware test beds. And that direct feedback loop is what allowed us to determine that the version 2 accomplished all of our needs to be safe for safing, and that going for a version 3 wasn't going to be worth our time or effort, especially since we needed to get something safe on board the rover on Mars. But once we did decide that version 2 was good enough, and we sectioned that off as a final build for our HOPE, we needed to conduct a final coordinated test to ensure that all of our capabilities were in place and that it was safe to run. There were no issues with our large-scale macro functionality. And we achieved that test campaign through 2 major methods. First was designing new test procedures to flex our new code directly, as well as some old code that lived directly on top of that new code and that dealt with the interfaces, as well as leveraging some of our old regression procedures that have been designed for previous flight software transitions to test, again, that macro functionality, the safer safing, fault protection, telecom, power, thermal, those big subsystems that didn't actually change with this flight software, as well as some more spot-specific things that our HOPE needed to do, in particular, being able to poke at the prime RCE that's broken with some cross-link diagnostics. In that full test campaign, the new procedures, as well as the old ones, took about a month with as many test bed engineers as we could supply, which is about 15 people. Next slide, please. And so our HOPE is on board MSL's RCE-A, and so we got to start thinking about operational constraints. As DJ talked about a lot, there are plenty of constraints on our HOPE, things that we are not allowed to do, namely use any of our science instruments or do things like drive or use the arm or our drill, things like that. But they weren't removed from the flight software. So most of those constraints are implemented through planning rules and conventions on the ground. So a little bit of increased complexity for planning when we get there, but we get to keep those capabilities. We may be able to release them, especially some of the more simplistic science instruments, for use at a future time, which is a major boon for us. Our next major constraint is that we are only going to be able to gather about 15 megabytes of data between downlinks before data loss becomes almost certain. And that's a data management regime that we've never seen on MSL, nothing even like it. And that drives a lot of our requirements that we're going to have for using this thing on flight. Third, it's worth remembering that we made great pains to make sure that the operations interface on our Hope is basically the same as all of our previous and future versions, which means the commands that we send up and the telemetry that we get back down is all almost identical. So all of our ground tools, as well as our institutional knowledge for operating this rover, are basically going to be used intact for our Hope, which is a major boon. And then the last 2 data points are basically showing that our Hope is on board. It's on RCE-A. We've checked out all of its memory partitions, and it's waiting for us to use it, which is a major reduction in risk for the flight for the flight vehicle now that we have at least one working backup. Next slide, please. Take a look real quick at some key dates. So important things here. Our last round of memory issues was in February of 2019. 2 months later, we had our first RHOPE concept presentation. Took about 8 months after that to finish development on the primary flight software, and then 11 months after that to do all of our testing, our final approvals on the ground, uplink the flight software, and install on the vehicle in December of last year. So about 19 total months of work, most of it completed during the pandemic and from home, with a bunch of people involved to various capacities. Next slide, please. Finally, we'll look at some lessons learned here, and then we'll get to some questions. So first, DJ already spoke to this, but the MSL flight software really, its modularity was key to this whole thing, making such low-level major changes to how these flight systems functioned, and then being able to see that the fault protection system basically just worked out of the box. A couple of minor changes here and there was really incredible, allowed our small team to make these changes really without having to worry too much about thinking that larger macro functionality. Second bullet, our process of the parallel development and dev testing with the hardware test beds in the development was really key to, number one, the speed with which we were able to do this development, but also being able to tackle some challenges in the hardware and the software interfaces that we just really didn't see coming. We were able to identify them live in the test bed and fix them as soon as possible, and that was a major boon for us. Skipping down, the strategy of shrinking NAND and then cutting over to NOR, so separating the changes to the file system from the changes to the hardware was a huge benefit to us, especially with a team that was relatively inexperienced with the specific code. It would have been difficult to track down bugs when we were changing everything all at once. And this really enabled us to make those changes quickly and effectively. And we'd recommend that strategy, I think, if any of you find yourselves in this. But I think at that, I'd like to end it and see if we can answer any questions.
Yeah, thanks a lot. Yeah, we do have a few questions that are in the Q&A section. The first, and I apologize for previously not mentioning the person's name, but our question here is from Steve Stolper. How did you manage the migration to the new data sizes and layout when the new software booted for the first time?
I think that's a question for Nick.
Yeah, good question. So we didn't. We actually wiped everything completely clean. There was no transition of data from one to the other. So we did some initial configurations, and we're going to be spending the next couple months getting things back up to speed exactly as we want them. But there was no migration, unfortunately.
Okay. Next question, also from Steve Stolper. What did the tasking model look like? Were tasks or threads added to the system in this process?
I'll get that. Hi, Steve, first of all. Sorry we can't have lunch at this conference. It's something I look forward to most of the time. I'll start by elaborating on Nick's. Nick kind of said, oh, there was no migration problem. I seem to recall 2 weeks in the test bed when we were fiddling with watchdog settings to make it a non-problem, part of that iterative development. He makes it sound a little easier than it was, I think. We didn't change the tasking model at all. That translation layer was built into the device manager as kind of indicated in the chart. So we didn't add any modules, we didn't remove any modules, and we didn't have to, and it's an event-driven system, not time-space partition, so we didn't have to modify any queue sizes or slices or anything like that. It was, fortunately, that wasn't an area we had to crack open.
Okay, great. It is 1:59. I'm not sure. Let's see. Maybe if we could take a really quick question. I'll read. The next one is from Calvin Giddens. Does the MSL code base use any sort of automated tooling to monitor for convention breaking code, such as that mentioned potential hard coding of memory addresses, size, scale?
Oh God, yeah. That was version 0.
Okay.
So the MSL team was very good about using static analysis tools. but it was 2014 was the last time it was uploaded, which means, you know, development was years before that. So one of the clever things we did in version 0, establishing a baseline, was, hey, let's use these new static analysis tools, which of course found all kinds of bugs in the old code, issues in the old code. And then we got to go through those and say, well, you know, we're trying to make as few changes as possible. Big theme on our hope was, don't change anything. If it ain't broke, don't fix it. Leave it be. The ops team already has a workarounds for God knows what, and changes ripple. So yeah, we ran at least 3 different static analyzers, including one that hadn't been run on the code before. And that made it actually difficult to establish a baseline. We did find some things that we actually found a number of bugs that we fed back to Mars 2020 and say, hey, you know what? We pulled their bug fixes in, we pushed ours out, and it was very cooperative. And I miss passing those people in the hallways.
All right. Well, thanks a lot. That was a great talk.